Hi, welcome back to McClutchy Maths. My name is Natalie McClutchy, and today we are going to be continuing our video series on networks and decision mathematics by looking at networks that are made up of processes. Decision mathematics is a branch of mathematics that uses networks in a variety of different contexts. In today's video, we'll be focusing on expressing processes using network diagrams. Processes occur throughout everyday life. It might be the process of an assembly line in a factory. It could be the work of multiple people on a project. It could even be the simple process of an individual baking or getting ready to work. Whatever the process is, we're interested in how we can complete it efficiently, at the lowest cost and in the shortest time. In today's video aimed at students in grade 12, we will explore how to create an activity chart, how to represent it as a network diagram, how to forward scan through the network, and how to determine the critical path, float time, earliest start time, and latest start time. So let's begin by looking at a fairly simple process. This is the process of me getting ready to go to work. And I've set this up in what's called an activity chart to begin with. On the first column, you can see the time that it takes in the process. So the first minute, the second minute, what's happening every minute as I go along for the first 10 minutes of my day. Then in the next column, you can see what the activity is. And then I've got a third column where I'm doing two activities at the same time. So I want to actually be able to represent this in an activity chart. So what that looks like is some slightly different headings here. I've actually got each of my activities, I'm labeling them with a letter, A through to J. So there's 10 activities, one for each minute. And then I've got the name of the activity, and then instead of having multiple columns when I've got activities working in conjunction with one another, I've got something called a predecessor. Now, a predecessor simply means the activity that must be done just before that activity. So if I look at activity B, which is storing my lunch in the fridge, before I can store my lunch in the fridge, I actually have to take it out of my backpack. So that's why activity A is the predecessor, the one that goes before activity B. And our fourth column is our time, how long that takes in minutes. So you can see from my original chart where I drank coffee for 3 straight minutes, well, we're actually condensing that down instead of 3 lines, 4th minute, 5th minute, 6th minute. That's now condensed to just time in minutes. Now, I'm going to talk to you a little bit briefly about what these kind of diagrams look like, because they're different to the kinds of diagrams we've been doing previously for networks when we were looking at things like Eulerian charts and Hamiltonian cycles and things like that. So in this particular type of diagram, we're not actually labeling our vertices, we're actually labeling our edges. So you can see that we've got a vertex at the very beginning that's an empty circle that represents our start, and then we move typically from left to right, or it can be from top down to the bottom of the process. Now you can notice that each of the edges is labeled with a letter. That's the letter of the activity, and then it's got a comma, and the number is the amount of time or the cost that's involved, or the number of people that are involved, or whatever it is we're actually measuring on our process. When we complete an activity, it bumps into the next vertex, which is another open circle. And then when we get to the very end, we represent the end with another open circle. So we've got these edges. Now, all of the diagrams that you'll see me draw here today will all have lovely, nice, neat parallel lines, but they don't always have to look like that. Some textbooks use curved lines to go around different activities. Some use arrows up and down. It really doesn't matter as long as you are representing the information correctly. So let's have a look at how we would do that with the process I've created. So as a little recap, so let's just quickly look at some key points here. You may want to make some notes. So firstly, our edges represent the activity that's taking place. The vertex is represented as a circle. It simply means it's the start of an activity and the end of the next activity. So they're not representing towns or places or anything like that. They're simply representing start of activity, end of activity. The numbers represent whatever it is we're measuring for the activity, the time or the cost of the activity. And we label the edges with a letter, not the vertex this time, because they're not places or people, it's activities. So that's very important distinctions. Also notice that different things are happening in this diagram. We've got activity B and C happening at the same time as activity A, and they're represented by edges that are parallel, running across one across the top of the other. That simply means that those activities are happening simultaneously or at the same time. And if we have a vertex in the middle of an edge, that simply represents that one activity has finished, the next activity starts immediately afterwards. So the activity before, in this example, is activity B. It's the predecessor for activity C. So some more things that are important to note is that usually we indicate our flow through the network using arrows. You can see this particular diagram below doesn't have arrows, but all of the ones that I'll be using for my worked examples will. So let's start by mapping out the activity of me getting ready for work. So step one, you're going to want some space. Sometimes some of these activities, they're very nice and linear and they lend themselves to a small amount of space, but typically you might want to set up about a third or a quarter of a page of your book. And it's a good idea in your middle of your available space to start with that opening vertex to start off with. And then what we're going to do is any activities that don't have predecessors are going to come straight out of that starting vertex. And we've really only got one. It's me unpacking my backpack. It's kind of the hinge point of the whole process. I can't do anything until that backpack is undone. Everything comes out of that. So that starting vertex is an open circle that's empty. It's a good idea to draw those circles so that you can write in them later on. We're going to find out what we actually have to write in there later. So make sure they're big enough to put some numbers into those. And then we draw a straight line out. That becomes our first edge. Our first activity is A, and then we put the time, which is 1 minute. Now we're going to close that off with another open vertex that will indicate that we're going to start some new activities, because we notice that storing the lunch in the fridge and powering up the laptop are both activities that rely on A being complete. So these are going to come out of that vertex. We've got B coming out and C coming out. Now it's important to note that sometimes you may not get your first diagram right. It might be a good idea to start it in pencil. However, you can't write in pencil in your external exams. So if you do write in pencil, you're going to have to go back over it in pen afterwards to make sure that it can be scanned for your external exams. Okay, so out of B flows activity D. D is boiling the kettle, and to do boiling the kettle, I firstly had to unpack the backpack and then put my lunch in the fridge. So they are the two predecessors that come before activity D. They flow into that part of that process. And running in parallel to that is activity C, powering up the laptop, and activity G, logging into the laptop. I'm doing that while the kettle is boiling. So that's why they are running in parallel. I'm able to multitask. Now, these activities are going to continue flowing along. I've got these two parallel processes going on. Now that I have boiled the kettle, I am going to make my coffee. And while I'm going to be making my coffee, at the same time as that, I'm going to be glancing at my emails, possibly on my phone or maybe on my laptop in the kitchen bench. And then running in parallel to all of that, I'm going to be nibbling on my breakfast, whatever that may be. So that's activity J. The only predecessor for J was A, that I had to unpack and get my breakfast out of my lunchbox first. So those three activities are now all running simultaneously with one another. And now I've got A, B, C, D, E. I'm missing activity F, which is drinking the coffee, and also activity I, which is replying to my emails. And that completes the whole process. That all now converges into that final vertex on the right-hand side. So let's talk a little bit now about what this diagram means. We're going to do a little bit of analysis, and we're going to have some new terms. So firstly, I'm going to look forward through my network to find out from left to right, when is the earliest I can actually start each of my activities. So this process is what we call forward scanning. Now, the way we do this is by looking at all of the previous activities, our predecessors, and we work back to the start of the process. So let's show how that's done. First thing you're going to want to do is split your vertices in half. Some textbooks do show it with a horizontal line, others with a vertical line. It really does not matter. Some even use half circles and not full circles. So You just do it the way that you're comfortable with, as long as you're splitting a half circle or a full circle into half, because we forward scan and we write our numbers on the left-hand side. And when we backward scan, next video, we're writing on the right-hand side. Okay, now our earliest start time is written on the left-hand side of every vertex. Now, if there's no immediate predecessor, then we have the value of 0. So that's our starting vertex. We start at time 0. Okay, now as I move along activity A's edge and I come up to the next point, 1 minute has passed, and that's that activity of me unpacking my backpack. So now that I've done that, I'm actually going to put that time into the left-hand side of the next vertex. So you'll note I've got the word capital and cumulative in big capitals. What that means is that as I'm going along the process, I take the left-hand side of the vertex before, I add the value of the activity, and that becomes the new value in the next vertex. So let's see how that's done. So where we can see that vertex that V and J and C is coming out of, we're going to put a 1 on the left-hand side. Now let's move along one of our edges. So we're going to move along this top edge first. I've got coming out of J into activity B, 1 minute passes, so 1 plus 1 is 2, then 2 plus 1 gives me 3, then 3 plus another 1 gives me 4. Now, I can't stop and put my answer in the last vertex because I've got to see what's going along on the other edges first. So let's work our way along the bottom. So now we've got activity C coming after activity A. We've got 1 plus 1 again makes 2, plus another 1 makes 3, plus another 1 makes 4. So this won't always be the case that you'll have the same numbers all over the place, but in this case I've tried to keep it super simple. So now I've got my top group of edges, which is my sub-process of making my coffee, and then I've got my bottom processes, which is logging into my laptop and replying to and checking my emails. So they both are going to take 4 minutes. Now along the middle, I've got me nibbling away on my breakfast, so 1 plus 3 there is going to equal 4. Along that top edge, the 4 plus activity F being 3 is going to make 7, and activity I will make 8. So I have this choice. What do I put in the last vertex? Do I put 7 from my top process? Do I put 4 from my middle process? Or do I put 8 from my bottom process? Well, the answer is you must put the maximum into that last one. So when we've got these multiple edges rejoining at a vertex, we have to choose the largest of our choices. That means we are going to put the number 8 into that last vertex. That's very important to note. So when you're forward scanning and you have multiple edges coming into a vertex, you always choose the biggest number to put in there. And the reason for that is that if you put one of the lowest ones in there, you're going to be saying that this process finishes here at the earliest, when in fact you've got other edges that aren't finished yet. So it won't finish there at the earliest. So what this whole picture is now telling me is that the earliest that I can finish getting ready for work is in 8 minutes. So now I need to write that as a statement. My earliest completion time for this process is going to be 8 minutes. Okay. We've got something new, some new vocabulary here, something called the critical path. And it's the special pathway, it's a unique pathway through the network that follows all of the activities that cannot be delayed. Because if I delay a single one of the activities on the critical path, my whole process is going to throw out. So this process at the moment is an 8-minute process, and ideally we want to keep it that way. We certainly don't want it to blow out, or that could ruin my day. So let's look through the network at the pathway that's causing it to be 8 minutes long. We found that when we were adding those pathways, we had a choice of our top pathway, our middle pathway AJ, and our bottom pathway, and we chose the number 8 to go in our last vertex, and that came from our bottom pathway ACGHI. So that is our longest pathway. It is the one that is causing the process to be 8 minutes long. If I make C or G or H or I, if any of those go any longer than the time that's allocated to them, the whole process is going to be more than 8 minutes. So that is our critical pathway. Now, if you're asked what is the critical pathway, you need to state it exactly as I've stated it. All the vertices, all the edges, including that very first activity A that was common as a predecessor for all of them. Activity A, C, G, H, I is your pathway for the critical path. And that was our process where we unpacked our laptop, powered up the laptop, logged into the laptop, checked the emails and replied to emails. And that makes sense. That can take quite a long time, sometimes more than 8 minutes. We've also got this new concept now as well, a new term called float time. And this is the maximum amount of time that you can hold off completing an activity and it won't throw the whole project out. So the only activities in a network that have float time are the ones that are not on the critical path. Because obviously, if I took longer to reply to my emails, the whole process is now suddenly longer than 8 minutes. However, you remember when we added up the top edges, it added up to 7 minutes, and that middle edge, which was pathway AJ, that only adds up to 4 minutes. So that difference between the total time of 8 minutes and the total time of that edge is what we call float time of that part of the process. So these two pathways shown in red all have float time. Every one of those activities there has float time. So if I was, for example, to follow this top pathway, and it was a 7-minute process versus 8 minutes on the critical path. What that tells me is the difference is 1 minute that I have up my sleeve. So I could take an extra minute on any one of those steps, B, D, E, or F. So for example, if I take just a little bit longer to make the coffee or just a little bit longer to put my lunch in the fridge, it's not going to throw anything out as long as I don't take more than a minute. I've got a minute up my sleeve of a bit of slack time. It's called float time. I could take 2 minutes to put my lunch in the fridge, which was activity B, instead of 1 minute, and I could still finish this whole process on time. Once again, also with that middle process, AJ, where I was eating breakfast, in that case, it only takes 4 minutes to eat the breakfast from beginning to end. So that means I've got 4 minutes up my sleeve. I can really take my time and savor that croissant or whatever it is that I'm eating. So I've got 4 minutes of float time on that middle pathway. So that won't affect the process if I took an extra 3 minutes to eat breakfast and took 6 minutes altogether for activity J, I am still going to finish the whole process on time, which is my objective. Now I'm going to talk to you about something called the latest start time. So this is the latest I could start a particular activity without delaying the whole project completely. So these are also following on from our idea of float time. The only activities that have a later start time are the ones on that critical path. So a little formula to do that is to look at the earliest completion time and take the activity time away from it. So for example, let's look at eating breakfast again. The latest I could start that is at the 8 minutes, take away the length of time that it takes to do the activity, the 3 minutes. So I could actually, instead of starting that at the 3 minute mark, I can delay that all the way to the 5th minute and then start it right at the very last chance that I've got, go hard and eat that breakfast for 3 minutes, and then I'm done by the 8 minute mark. So the latest I can start eating breakfast is at the 5 minute mark. And also for coffee, let's have a look at activity F. The latest I could start that is 5 minutes into the overall process. So I'm working backwards here from that next part of the process, take the 8, take the 3 away, and that gives me a 1 minute delay. So basically, instead of starting at the 4 minute mark to drink the coffee, I could start it at the 5 minute mark, because remember there was 1 minute of float time in total on that top pathway. So my latest start time is at 5 minutes. Right, let's have a quick chat about what's coming up next in this video series. We've just finished forward scanning. In my next video in this series, we're going to look at how to backward scan through the network, and we are going to recap in that video critical path, float time, earlier start time, later start time. So all of these terms that we've come up with today, we're going to have another look at those with a new worked example. So please click on the next video. It's right there waiting for you to watch. We're going to look at dummy edges as well in that next video. It's the one with the pictures of the cupcakes on the front. Then we're going to talk about some flow networks and look at maximum flow, minimum cut. These are already filmed, so go ahead and have a look. Hungarian algorithm and minimization and maximization. Not a lot of textbooks cover maximization with the Hungarian algorithm, so that is one you are going to want to see. That could end up being on your external exams. Well, I'd like to say thank you so much for joining me today here at McClutchie Maths. My name is Natalie McClutchie. Welcome to all of our new subscribers on the channel. Why not follow us on Facebook and Instagram? Look for us there for McClutchy Maths. And if you have any questions, you can email me at mcclutchymaths@yahoo.com. You can also message me on Facebook Messenger or direct message me on Instagram as well. Worthwhile catching up with me there because we do have little videos, bloopers from time to time, tips, tricks, and some memes and fun stuff like that. So thank you again for being here today. I really appreciate your feedback and all of the love and support that you show. Have a wonderful day.